to this point in your mathematical education, you've learned single variable calculus. Calculus involving one dimension at a time, right? One single variable. But in this class, we're going to learn multivariable calculus. Calculus over multiple dimensions at a time. And to that end, we're going to need to develop a mathematical framework to describe behavior in multiple dimensions. To be able to do this, we're going to define a new mathematical structure. We're going to call it the vector. A vector is a quantity with two things. With a direction and a magnitude. Okay, magnitude here, just a fancy word for length. Okay, so two things, direction and magnitude. Note in particular that we make no mention of position. So a vector, we focus on direction and magnitude, but not position. So let's illustrate a vector in 2 dimensions. In this section, we'll focus on 2 dimensions, so many of the ideas that we develop can be applied to 3 or even higher dimensions. Okay? So we're going to focus on 2 dimensions. 2 dimensions we notate with R2. This blackboard bold R stands for the real numbers. Okay? If I leave the 2 off, that's 1 dimension. But with the 2, it's 2 dimensions. Okay? And 2 dimensions we can illustrate with a plane. So let's imagine we're working in this plane. Okay? So direction and magnitude, we can illustrate that with an arrow. So maybe we have this arrow here. Okay? This arrow is a vector. I can even give it a name. When we label vectors in this class, when I do it on paper or on a blackboard or on the screen, I'm going to label it, give it a variable name, and then I'll put a little arrow above it to emphasize that it's a vector. In your book, they will often use a bold letter. Okay? So if it's a bold letter, that also represents a vector. Harder for me to do that on the screen or on a blackboard or on a piece of paper, so I'll use the arrow notation then. But in your textbook or in your homework, they will often use that bold letter to represent that we're dealing with a vector. Okay? So notice this arrow does represent a direction, right? It's pointing a certain direction. And the length of the arrow communicates a magnitude. Okay? How long is the vector? But notice I've also drawn it in a particular position. I could draw a vector with the same direction and the same magnitude. Okay, but I draw it in a different position. How does this vector relate to the original one? Well, remember, vectors don't have position. So these 2 vectors are actually the same vector. They're exactly the same. I've just drawn them in different positions. What a vector communicates is a change in position. If I draw it here, it means that I'm changing maybe from this position to this position. If I draw for this vector, I'm changing from this other position to this other position. But the amount of change is the same. Okay? This idea of vectors is actually an extension of how numbers work in 1 dimension. So let me give you an example. Okay, if I tell you that I went out and I spent $300 on a new TV, well, what does that tell you? Does that tell you how much money I had? Or how much money I now have? No, it tells you the change in the amount of money I have. Right? This is the amount of money I started with. This is the amount of money I ended with. I don't know those quantities, but I know the change. I know that I lost $300 in this transaction, in this process. And that negative 300, that represents a magnitude, right, $300, and a direction. I lost that money, right? It is a negative amount. And so this quantity is, in that sense, a vector, right? I could have any amount of starting money, right? I could have $500, I could have $500,000. But this will always be pointing the same direction if I buy that TV, and it'll always be the same amount, right? So it doesn't have a position, but it has a magnitude and a direction. It is a vector. So how we use numbers in one dimension is the same way we want to use vectors in these higher dimensions. Okay? One more example. Even if we do have a position, often we can think about these numbers as vectors. Okay, if I say I have 30 apples, okay, we imagine a baseline, a starting position. In this case, we understand that 0 apples is kind of the default position, right? But if I have 30 apples, I could think about that as a position and a magnitude away from that starting position. A direction and a magnitude away from that starting position. Okay, and that gets me to how many apples I have now. Okay, so this, I could think about this as a vector still, even though there is an implied starting position. The change is a vector. And if I change the starting position, if I have 30 more apples from where I started from, maybe I already had 100 apples. Now if I have 30 more apples, that's just telling me a direction and a magnitude. So we often think about numbers intuitively as vectors. So what we're going to do here is we're going to extend the ideas from these one-dimensional numbers to these higher dimensional vectors, which is one of our favorite things to do in mathematics, is to extend a simple idea that we understand well to some more general framework. By understanding that vectors are just an extension of the number system we're already familiar with, it gives us a framework for developing operations on these vectors, like addition and subtraction. So let's see how that would work here. So what does it mean when we add two numbers in our single variable system? So say I get $20, and then I make another $10. So if I add those two together, what do I get? Well, I get $30, and if I think about it as magnitude and direction, that means the total amount I've traveled is just both of them put together. Right? The total amount of money I've earned is both of them put together. In terms of arrows, I just put the two arrows together and I combine them into a single arrow. So how would that work in, say, 2 dimensions. So say I have one vector, let's call it u, and I have another vector v. And I'm going to draw these much how I drew them in the single variable case, tail to tip. So notice the tip of u and the tail of v are at the same point. I can do that because remember, vectors don't have a position. I could draw them wherever I want, right? As long as I get the direction and the magnitude right. But if I add these together, what would I expect to get? It helps to think about this as maybe traveling. If I travel in direction u, and then I switch and I travel in direction v, okay, where do I end up? That's what the vector should communicate, just like it does here. If I have $20 and I add $10, where do I end up? Well, I have $30. If I go here and then I go there, where do I end up? I end up traveling the net amount of displacement is this right here. Okay, that vector right there. So the sum of 2 vectors should be interpreted this way. What about subtraction? So let's approach this the same way. Let's first think about how subtraction works in the single variable setting and then apply it to the multivariable setting. So in the single variable setting, say I start with $50. Okay. And then I'm going to subtract $30. So let's have $30, and I'm going to draw it with the same starting position. Okay. So if I subtract these two, what would I get? Well, I'd get the difference, wouldn't I? The difference from here to here. That would be 50 minus 30, right? What's ever left over. Okay? What does it take, in other words, to get from here to here? Okay? In 2 dimensions, we want to have the same kind of behavior. Okay, so if we're in the plane, and I have one vector u and another vector v, if I subtract these, then I want what it takes to get from here to here. Okay, this new vector is u minus v. Notice it's the order here matters, okay, because direction matters. So it's not this guy, okay? It's always end minus start. The resulting vector is end minus start. Okay, so the first guy in your subtraction, that's where the resultant vector will end up. The second vector in the difference, that's where the resultant vector starts from. So u minus v, I end up at the tip of u, I start at the tip of v. Okay, and that's exactly how it works in the single variable case also. For this guy here, end minus start. This vector ends at the tip of my first vector, at the 50, and it starts at the tip of the vector I'm subtracting, the 30. Next, let's think about multiplication. Now, we have to be a little careful when dealing with multiplication here. So let's think of what it means in the one-dimensional case first, as usual. So if I have some vector here, okay, and let's give it a value. Let's say it's 2. Okay, what happens when I multiply it by, say, 3? How do I interpret that? So we know what 2 times 3 is. It's 6. But one way to think about that is that I'm stretching out this vector that I have here, this direction and magnitude. I'm stretching it out so it's 3 times longer than it was. So it's 1, 2, 3 times longer than it was. So that's 3 times 2, which is 6. Notice that the role this number is playing, let me use a different color, the role this number is playing and the role this number is playing are a little different, right? This is giving us direction and magnitude, whereas this is stretching out the first number, okay? We're thinking about them differently. Okay, let's take that now to the multidimensional setting. And I want to do pretty much the same thing. If I have a vector, let's not make it quite so long, maybe like that. Okay, let's call this vector u. Okay, now the way we're thinking about multiplication here, it doesn't make sense to multiply a vector by another vector in that way. But this kind of stretching operation, that does make sense. If I want to take a vector and stretch it so it's 3 times as long as it was before, then I could do something like this. 1 time as long as it was before, 2 times as long, 3 times as long. Okay? And that would be 3u. Notice I'm taking my vector and I'm multiplying it by a plain old ordinary number, not by another vector, right? This is called scalar multiplication, and these plain old ordinary numbers, when we use them in this way, we call them scalars because they are scaling the vector, okay? So these guys here are called scalars. This is a scalar. Okay, let's look at another example. Let's do this one. Okay, let's call this vector v. I don't have to multiply by just 3 or just whole numbers. I can multiply by something less than 1. What if I multiply by a half? Well, that would make it half as long as it was. So 1/2 v is half as long as the original vector v. I've multiplied it by the scalar 1/2, and now it's half as long. Okay? I could even multiply it by negative numbers. So let's say I have a vector w. Let's not make it quite that long. There we go. Vector w, what happens if I multiply it by, say, -2? Well, if I were to multiply this by -3 instead of +3, I'd still get 6 as the magnitude, but it'd flip it around so it ends up in the opposite direction. It'd be pointing the opposite direction. The same thing happens here. If I multiply by a negative, the length changes as normal, but the negative flips the direction. And so now I'm 2 times as long as I was before, and because of the negative, I'm facing the opposite direction. Okay? That's how scalar multiplication works. It scales the vectors. Okay. By the way, you can think about division also, but if you have division, if you have like a vector divided by 3, the way we really think about that is 1/3 times the vector. So we always go back to scalar multiplication. Okay. Notice we cannot divide by the vector. We could divide by the scalar because we could interpret that as multiplying by 1/3. But it doesn't make sense to divide by a vector. Okay? So far, whenever we've represented a vector, we've done so using arrows, right? And, geometrically, this makes good sense. An arrow communicates direction, it communicates magnitude. But ideally, we would like a more precise way to talk about these vectors rather than just sketching an arrow on a page. We want to be exact here, okay? It turns out there's a very natural way to describe vectors if you are in a coordinate system, okay? So let's sketch a coordinate system here. Now, as a reminder, it doesn't matter where this vector is in the coordinate system, right? Vectors don't have a position. I could draw this same vector at any point in this coordinate system, and I'd have exactly the same vector. Okay? These two vectors, exactly the same. They're pointing the same direction. They have the same length. So how do we represent this? Well, we notice that in this coordinate system, we can break it into pieces. We could say, this vector, the total displacement that we see with this vector is 3 units in the x direction and 2 units in the y direction, from its tail to its tip. And that's true no matter where we place the vector. 3 units of displacement in the x direction, 2 units in the y direction, from tail to tip. These are the components of the vector, and it gives us a way to describe the vector. We can write this vector similar to how we would write an ordered pair of point, by just writing how much the displacement is in the x direction and how much displacement in the y direction we have. And to emphasize it's a vector, instead of using parentheses where we would use a point, we use angle brackets. And that emphasizes that we're dealing with a vector. When we write a vector like this, we say it is in component form. Notice in particular that if I draw the vector with the tail of the vector at the origin of the coordinate system, then the tip of the vector ends up at the point that is equivalent. The coordinates of the point are the same as the coordinates of the component form of the vector. When we sketch the vector like this with the tail at the origin, we say the vector is in standard form. If we don't have a good reason to draw the vector somewhere else, this is usually where we draw the vector, with the tail of the vector at the origin. And it makes it real easy to determine the coordinates because the point the tip is at will always be have the same coordinates as the coordinates of the vector in component form. But component form isn't the only way we can represent a vector. In fact, the way we've drawn it here suggests a different way that we can represent a vector. It's similar to this in that we kind of disaggregate it into how much we move in the x direction and how much we move in the y direction. But we emphasize those individual movements a little bit more. Okay, so what I could do is I could think about moving along the x-axis and separately moving along the y-axis and then adding them together to get the final movement. Okay, so remember this is the vector we want here. In fact, let me blow it up a little bit for emphasis. This is the vector we want here. Okay. Now, I can think about a vector in this x direction. And let's give this vector a special length. Let's give it length 1, and I'm going to give it a special name too, because this direction is important. It's a very basic direction. It's direction I. Right? And so if this vector is, what is it? 1, 2, 3, 4, 5, 6, 7, then 1, 2, 3, 4, 5. So this vector here in component form is 7, 5. But I can break this up into two different movements. I can move in the x direction, in this direction, right? If this vector here has length 1, we call a vector of length 1 a unit vector, then if I repeat that movement 7 times, I'll get all the way over here, right? In fact, let me give it a different color. I. Okay? And I'm going to combine it with a movement in the vertical direction. A vector, let's take a vector that is pointing straight directly in the positive y direction and also has length 1. We give this vector also a special name. We call it vector j. Okay? And I could draw it there, or I could draw it here, because remember, vectors don't have a position. Okay? So if I want to get all the way to the tip of vector v, I know that I can move 5 units in that y direction. And since this already has a length of 1 unit, if I multiply it by 5, if I do this 5 times, if I scale it so it's 5 times as long, it will have a total length of 5 when I'm done, right? So 5 times my unit vector j, because it's a unit vector, is length 1. 5 times j will have a total length of 5. So putting these together, going this direction and then going this direction, notice I end up in the same spot, right? And so another way that I could represent vector v here is 7 times vector I plus 5 times vector j. We call I and j the standard unit vectors. They are the vectors of length 1 that point along the positive axes. I points in the positive x direction, j points in the positive y direction, and they both have length 1. So standard unit vectors. Okay, and we're just doing a vector addition here, right? I'm getting 7i, that's one vector. It's pointing in the x direction, 7 times as long as it was before. This is a vector, points in the j direction, and then I multiply it by 5, so it's 5 times as long as it was before, so its total length is 5. And when I add them together, I know that this vector is the sum of this and this. So this is another way to represent vector v. Both of these are equivalent. I personally prefer this form, and I think most mathematicians prefer this notation for a vector. But this is quite common in certain applications. Physics, for example, they really like this format. Either way is equivalent. You will see both in this class. We will go back and forth. We may see this one a little more than this one, but both forms will be used, and you should be able to use either form to represent your vectors and to manipulate your vectors. Now that we know how to represent vectors numerically, let's learn how to add, subtract, and scalar multiply numerically with these vectors. Okay, so a couple examples. Let's let u equal 2, 4, and vector v equal 3, -6. And let's add these two vectors together. Let's call the sum vector w. Okay, so to numerically add vectors together is real simple. You just add the corresponding components. So we want u plus v. Vector u is 2, 4. We're going to add that to vector v, which has components 3, -6. And I'm just going to add corresponding components. So first component plus first component, that's 2 plus 3, which means the first component in my resultant vector is 5. And now second component. Second component, 4 plus second component, -6. 4 plus -6 is -2. So that's the second component in my resultant vector w. And we're done. Okay? Let's go ahead and graph these using our arrows to make sure that the addition operation that we want matches the vector we get here. Okay? Remember, we have a very specific understanding of what vector addition means. Okay? So here's my x-axis, here's my y-axis. We're going to start by plotting u in standard position. So I'm going to plot u with its tail at the origin. So 2, 4. So I'm going to go over 1, 2, and then up 1, 2, 3, 4. So there's vector u, 2 to the right, 4 up. And then when illustrating vector addition, it's usually a good idea to draw the next vector, vector v in this case, tip to tail with the previous vector. So I'm going to draw vector v, start with the tail of v at the tip of u. Okay, so v is 3, -6. So I'm going to go 1, 2, 3 over, 1, 2, 3, 4, 5, 6 down. Okay, and now finally let's draw vector w, 5, -2. I'm going to again draw it in standard position. So 1, 2, 3, 4, 5 over, and then -2, so 1, 2 down. And notice it makes a triangle. And that's what we expect, right? When we add the two vectors, vector u plus vector v, it should be like we walk this path and then walk this path, and then the sum should give us a straight path to get to the same position. Okay? That's how I think about vector addition. If I walk this way and then walk this way, if I add those two vectors together, it gives me the direct path to get to the same position. Okay? All right, let's do another example with vector subtraction. Let's let vector A be 3i minus j, and let's let vector B be 2j. Let's find vector C, which will be vector B minus vector A. Okay? Notice we've written these vectors in terms of the standard unit vectors. Vector A here, of course, if I write it in component form, would be 3 for the first component, and then the value in front of J is -1, so -1 for the second component. For B here, if I write it in component form, notice I don't have an I. I could think about that as 0i. So I go 0 units in the x direction, and then 2 units in the y direction because it's 2 times j. Okay, so those would be the vectors in component form. So vector C is going to be the difference of vectors B and A. So I'm going to subtract A from B. Vector B is 2 times j. And I subtract A, which is 3i minus j. And to subtract these, I just subtract corresponding components, just as I have done. In this case, my corresponding components have the same vector, right? They're multiplied by the same vector. Essentially, you are just combining like terms, okay? So so I have no i's, minus 3i, that gives me -3i, okay? And then 2j minus -j, combining the like terms, that's 3j, okay? You'd get the same thing if you did this in component form. If you did this in component form using these notations, vector B is 0, 2, minus vector A, which is 3, -1. And here you just subtract the corresponding components. 0 minus 3 is -2. And 2 minus -1 is 3. Wait, I think I got a little ahead of myself. 0 minus 3 is -3, of course. And 2 minus -1 is +3. Okay, gives me the exact same thing. Okay, just a different way to represent the notation. Different way to represent the vector. As a rule of thumb, if the problem starts with vectors in using the standard unit vectors, you should probably write the answer using the standard unit vectors. If the problem uses vectors written in component form, you should do the problem in component form. That way you could get used to both notations. Okay, let's go ahead and graph these, and we can compare the answers that we get with the geometric representation we expect. Okay, so A is 3i minus j, so I'm going to draw that in standard position. So 3i, that means 3 units in the x direction, 1, 2, 3, minus j, -1 units in the y direction. And then B is just 2j. Label this first. B is 2j. And so that's no movement in the x direction, but 2j means 2 units in the y direction. So 1, 2 units in the y direction. Okay? Now remember what vector subtraction should give us. It should give us a vector that with its tail at the second guy and its tip at the first guy, right? N minus start. So let's draw our resultant vector, vector C, with its tail here, since this should be the start, right? N minus start, A should be the start. So tip of A, and I want to go -3, 3, right? -3 units in the x direction, 3 units in the y direction. So 1, 2, 3 units in the negative x direction, 1, 2, 3 units in the y direction does indeed complete our triangle. Vector C here, which is b minus a, end minus start. I ended up at vector b. I started at the tip of vector a. So the arithmetic again matches our geometric interpretation that we wanted. Okay. All right, let's just do one more quick example with scalar multiplication. Let's let u equal 2, 3. Find for u. Okay, well, that's easy enough. For u is just 4 times vector 2, 3. And all we do for scalar multiplication is we multiply each component in the vector by the scalar multiple. So 4 multiplies the 2. 4 times 2 is 8. That's going to be my first component. And then 4 times the second component, 3. 4 times 3 is 12. And so the scalar multiple is 8, 12. Okay, let's see if it jives with our representation, our geometric representation. What we expect to happen is we expect to have our vector u, and then this should be 4u, should be 4 times as long as our original vector u. Okay, so 2, 3, that's 2 units in the x direction, 3 units in the y direction. Okay. And now this guy should be 4 times as long, so let's see. 4u is 8, 12. So also in standard position, 1, 2, 3, 4, 5, 6, 7, 8 in the x direction. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 in the y direction. And notice it's pointing in exactly the same direction, right? They are exactly lined up, the two vectors. And this really is 4 times this one. 1, and what was it? 2, 3? 2, 1, 2, 3, 2, 3, 3, 4. Okay, so that for u really is 4 times as long as the original vector u. Remember that a vector has 2 pieces to it. It is a direction and a magnitude. A very natural question, as it turns out a very useful question, is can we isolate each of these components of a vector? Can we take a vector and in some sense isolate the direction of the vector, or in some sense isolate the magnitude of the vector? The answer is yes, and it's actually fairly straightforward to do. We're going to start off with the magnitude of a vector. How do we find just the magnitude of a vector? How do we isolate it? So let's imagine we have a vector with components a and b. Okay? So if we were to sketch this vector, then what does it mean for the components to be a and b? Well, it means that if we look at how far we travel in the x direction, we go a units. And if we look at how far we travel in the y direction, we go b units. That's the net change in those 2 directions. Okay? And if we look at this, well, heck, that's a right triangle, isn't it? And so we can use the Pythagorean theorem to find the length of the vector. So by the Pythagorean theorem, the length of one leg squared plus the length of the other leg squared is equal to the length of the hypotenuse squared. Now I do want to caution you, this is not v squared, because remember v isn't a length, v is a vector. According to the Pythagorean theorem, the result over here is going to be the length of this side squared. Okay? So we actually have a special notation for the length of a vector. It's like an absolute value, but instead of 1 bar, we have 2 bars. So it's like these double absolute value bars. This is the length or the magnitude of vector v. And it actually has a few names, magnitude or length, but those two absolute value bars is called the norm operator. And so sometimes we also call this the norm of v. And finding the magnitude, applying that operator, we sometimes call it taking the norm. And so according to the Pythagorean theorem, it's one leg squared plus the other leg squared equals the length of the vector squared. Okay, so this magnitude is what we're looking for. Now right now it's squared, so all we have to do is unsquare it. And so the norm of the vector is just the square root of a squared plus b squared. And since it's a distance, we don't have to worry about the plus or minus. We know it'll be a plus. It's a distance. Okay? So this is the formula for finding the magnitude or the norm of a vector v. And it should look familiar. It's just the distance formula, right? And all it is the sum of the squares of the two components of the vector under a square root. And that's how you find the norm of a vector. Now, before we move on to finding the direction of a vector, there is one useful property of the norm that is worth mentioning. Okay? If you have a scalar multiple of a vector, how does that scalar multiple affect the norm? Okay, so instead of v, what if I have some scalar k times vector v? How would that change the norm? So my new vector is ka times kb. Well, the norm of kv, according to my formula, is equal to the square root of the first component squared. So my first component in this case is k times a, plus the second component squared, which is k times b. And, you know, that's the answer technically, but let's see if we could simplify it, okay? Because this product is together squared, we could square each of the factors individually. So k squared a squared plus k squared b squared and now they have that common k squared, so I could factor that out and give it its own square root. So k square root of k squared times square root of a squared plus b squared. So what's the square root of k squared? Now do be a little bit careful here. It's very common to say, oh, square roots and squares, they cancel. It's not quite true. It depends on the sign of k, right? Because if I have square root of 2 squared, well, 2 squared is 4, and square root of 4 is 2. Great. Square root and square cancel. Okay? But if I have the square root of a negative number squared, that negative, when I square it, it turns positive. Square root of 4. And this symbol means the principal or positive root of 4. The positive root of 4 is positive 2. In this case, the square root and the square did not cancel, right? Notice this symbol, this square root symbol, this principal root symbol, it always spits out the positive root. And so generally, if I have the square root of some number squared, it will spit out the positive version of this number, or the absolute value of that number. Okay? So square root of k squared is going to give me the absolute value of k. And square root of a squared plus b squared, well, hey, that's just the norm of the original vector v. And so when we scalar multiply a vector, all it does is it scales the magnitude of that original vector. Okay? That's your new magnitude. Notice that this does make sense, right? Because we know if we multiply a vector by 5, it's going to be 5 times longer, right? We just have to be aware of that absolute value, because if I multiply by -5, it's 5 times longer, but it flips in the other direction, right? If all I'm looking for is the magnitude, I don't care what direction it's in, it's still 5 times longer, okay? And that's, we have to be aware of that absolute value. But this occasionally is a useful formula. If you have a scalar inside the norm, you could take it out of the norm as long as it's inside an absolute value. Okay? So we know how to find the magnitude of a vector. How do we isolate the direction of a vector? Now, the first thing you might think of is, well, hey, why don't we grab the angle of the vector, right? If I have a vector, why not just grab the angle it makes with the x-axis? Okay? Now, it's a good idea. It will tell us the direction, right? I could change the length of this vector all I want. That angle stays the same. There are a few problems with it, though. The biggest problem is that it works okay in 2 dimensions, but it doesn't work very well in higher dimensions, 3 or 4 or 5 dimensions. We really would like a framework that can apply to any number of dimensions, not just applies to just 2-dimensional space. Okay, so angle isn't what we want to go with. We need some other way to describe the direction of a vector. Now, the vector is already pointing the right direction, right? What if we use a vector to describe the direction of the vector? We just need to kind of strip out the magnitude in some sense. So this is what we actually end up doing. We're going to do what we call normalize the vector. Okay, be careful with the terminology here. We just learned that when we find the length of a vector, it's called taking the norm of the vector. This word has kind of the same beginning, norm, but it means something very different. Okay, so just don't confuse norm with normalize. Normalizing a vector is taking the vector, but changing it to a unit vector. This means changing a vector to a unit vector. A unit vector is a vector of length 1. That allows us to keep the direction, but it kind of sets a default length that is easy to work with. It's very easy to work with a vector of length 1. It strips out the magnitude from the original vector. Okay? So how do we normalize a vector? How do we change it into a vector of length 1? Well, if I want to take this vector here and change it into a vector of length 1, notice it'll be pointing the same direction. All I'm doing is I'm squashing it down, or if the original vector was short, I might be stretching it out. Okay? I'm scaling the vector, in other words. So if I want to normalize the vector, I want to scale the vector so it has length 1. So let's take our vector, let's multiply it by a scalar, and we need to figure out what this scalar needs to be so that the total length of our new vector is 1. Okay, so let's find the length of this and then solve for k so that the total length of this is 1. Now, we just learned that when we multiply by a scalar, I could pull that scalar out and throw it into some absolute values. Okay, so this will be the absolute value of the scalar times the original length of the vector. And because we want to normalize the vector, we really want it to be pointing in the same direction, not the opposite direction. If the scalar is negative, that's going to cause the scaled vector to point in the opposite direction, to flip around, right? We want it to be pointing this way, not in the exact opposite direction. So that means if we want it to be pointing the same direction, k should be positive. So we could drop the absolute values because we already know the k we want is positive. So if we can find that k, we can figure out how we can scale a vector to changing into a unit vector, how to normalize it. So let's just solve for that k now. Divide both sides by the norm of the vector, by the length of the vector. And that tells me that the magic scalar I should multiply by is 1 over the length of the vector. If I multiply a vector by 1 over the norm or the length or the magnitude of the vector, I will get a unit vector, a vector of length 1. So to normalize a vector v, we take that vector v and we multiply by 1 over the norm of v. Okay, so make sure you understand what's going on here. This is a vector, but this is a scalar, right? V is a vector, but then we're taking the norm of v. So we have 1 divided by just a plain old ordinary number. We get another plain old ordinary number, a scalar. And if I take that and multiply it by v, scalar multiply it, it'll change the length so that the length of this new vector is length 1. Okay, it's a unit vector. And unit vectors, as we will see, are going to be real convenient to work with. Let's take a look at an example that puts together some of the ideas that we've learned. We want to find a vector w that points in the same direction as another vector v, which is negative 8i minus 8j, with magnitude 5. Vector w should have magnitude 5. Okay, so first off, this vector is in terms of the standard unit vectors, right? Remember that if we were to write this in component form, this would be negative 1, negative 8. The scalar in front of I, that's your first component. The scalar in front of j, that's your second component. Okay? Now, we want to find another vector. We want it to point in the same direction as v, but with a different length. So do we really care about the length of v at all? No, right? We won't only care about the direction. We want to preserve that direction. We want to get rid of the length. So how do we preserve that direction and get rid of the length? Well, we need to normalize it. We want to turn it into a unit vector. So let's start by normalizing v. Okay? So to do that, we want 1 over the norm of v times v. If you think about the formula, it does make sense, right? The length of this is the norm of v. So we want to scale it so that we take away that length. We divide by it. We're shifting it so it undoes the length we already have. Okay? By the way, you can also write it, and we frequently do write it this way. Means exactly the same thing. Okay? All we're going to do is we're going to take 1 over the norm of v. So we got to take 1 over norm of v. That's going to be square root of the first component squared plus the second component squared. Looking at those components of v. Okay, that's the norm of v right there. And then we multiply by vector v itself. So this is actually going to be the vector, which I will leave here in terms of the standard unit vectors. Okay? So let's simplify. Negative 8 squared is 64. Negative 1 squared is 1. So I get square root of 65. Unfortunately, that root doesn't simplify. It is what it is. It's a nasty square root. Okay? Let's go ahead and multiply that through, distribute it through. I get negative 1 over square root of 65i minus 8 over square root of 65j. That is vector v normalized. This vector points in the same direction as vector v, but now it's a unit vector. Now this is a unit vector. Okay, so now we've isolated the direction of vector v. Now we're not done yet though, right? We want vector w, and we don't want it to have length 1, we want it to have length 5. Right now this is a unit vector, it has length 1. So how do we change a unit vector with length 1 into a vector with length 5? And keep the direction? Well, we want to scale it again, right? Scaling changes the length. And since it has length 1 now, if I want its total length to be 5, that means I want it to be 5 times as long as it is now, right? 5 times as long as something is with length 1 has length 5. So vector w will be 5 times that vector I have now, that unit vector. That way I keep the same direction, but by multiplying by a new length, that new length will be the length of the resultant vector. So if I multiply that 5 through, I get negative 5 over square root of 65i minus, and then 5 times 8 is 40 over square root of 65j. And that's my final answer. Or if you prefer it in component form, negative 5 over square root of 65, comma, negative 40 over square root of 65. It means exactly the same thing. Okay? That is now a vector that points in the same direction as the original vector v, but it has length 5. Let's take a look at another example. An airplane flies due west at an airspeed of 420 miles per hour. The wind blows in the direction of 30 degrees south of west at 50 miles per hour. What is the ground speed of the airplane? And what is the bearing of the airplane? Okay? So for this problem, we're told the airspeed of the airplane. That airspeed is the speed of the airplane relative to the air it's moving in. If you were moving with the air, the plane looks like it's going 420 miles per hour west. But the air is also moving, right? It's moving 50 miles per hour, 30 degrees south of west. Okay, west is to the left in our diagram, so we move south of that, which is why we go this way. Okay. So we want to know two things. What is the ground speed of the airplane? So for that, we need the airspeed plus how fast the air is moving that it's flying in. So we need to add these together. These are vectors. Okay, so if we can add them together, it will tell us the total speed of the airplane, the direction and the speed of the airplane when you put it all together. But they're not written right now in a form that would make it useful in the way we're used to seeing vectors, right? We just have an arrow, we're told, hey, it's west, and we're told how much. Technically, that is direction with magnitude, but it's not the usual format we see vectors in, right? Same thing here. We have the length, the magnitude, 50 miles per hour. We have the direction, 30 degrees south of west. But again, it's not the form we're used to. So let's start by converting these to the kind of format that we're used to. So I'm going to have the airplane speed, or the airplane motion. I'll call that A. Okay? And it's moving 420 miles per hour to the west. So if we think about the XY plane like this, then that means it's moving down the negative x-axis. Okay, so negative 420, and then no movement at all along the y-axis. Okay. And what about the wind speed? I'll call that W. This one will take a little bit, just a little more effort. We have to construct a little triangle here. Okay. Now, 30 degrees, that is an angle that we know. Generally, the ratio of the sides for a 30, 60, 90 triangle are 1, 2 square root of 3. Okay, and the smaller sides are opposite smaller angles, bigger sides opposite bigger angles. That's how I always remember which side's which. Okay, 30 degrees is the smallest angle, so 1 is opposite that smallest angle. 90 degrees is the biggest angle, so 2 is the biggest value. So 2 is opposite that angle, and then this is 60 degrees, so root 3 is opposite that one. Okay? But the way we've written our axes, we'd be in quadrant 4, and so I am in the negative x and the negative y direction. Now, these, of course, are just the ratios of the sides. The actual length of this side here should be 50 miles per hour, right? So we would have to adjust everything to meet that. So if this is 50, okay, negative 1 is half of 2, so this side should be half of 50, right? So 25 and then negative. And then this side, a little bit trickier. The easiest way is to know, hey, this is 1 times root 3. So this is going to be negative 25 times square root of 3. Okay? All right. So that's the real sides of this triangle with this one edge at 50 miles per hour. Okay? And with that, we can figure out the vector. I'm moving in the x direction, negative 25 root 3 miles per hour. And the wind is blowing in the y direction, negative 25 miles per hour. And if you were to check, I won't do it, but if you want to check, the total length of this is 50. And so the total speed of the wind is 50 miles per hour. Okay? So this describes the motion of the airplane, the velocity of the airplane in the air, and this describes the velocity of the air. So if we add them together, that will give us the total velocity of the airplane relative to the ground. So I add them together and get kind of a nasty expression. Negative 420 minus 25 square root of 3, comma, negative 25. Right? That's the best I could do right there. It's not the prettiest thing in the world, but it is what it is. Okay? So now we have a vector that describes the motion of the airplane, the velocity of the airplane relative to the ground. I know the direction it's in, and I know how fast it's going relative to the ground. Okay? So now I want to know, what is the ground speed of the airplane? Okay? So I want to find the magnitude of this resultant vector. Let's give it a name. Let's call it total. Okay, so I want to find the magnitude of this guy. That'll tell us the total ground speed of the airplane moving in this direction. Okay, now this is nasty enough that we want to use a calculator for this. So that's what we'll do. But let's set it up. This is going to be the square root of this guy squared. Negative 420 minus 25 root 3 squared, plus the other component squared. Okay, so let's plug into a calculator. I have one off to the side here. Okay, all I'm using is the Desmo Scientific Calculator. It's a great calculator. I recommend it. So I'm going to use the square root of negative 420 minus 25 square root of 3. And I square it, plus negative 25 squared. It's all under the square root, and I get 463.975287. That is the total ground speed of this airplane. $463.975287 miles per hour. Okay? So that's question 1 answered. Question 2. What is the bearing of the airplane? Okay, so that's the direction, and we have a direction here, and if we want to, we can normalize it, get a unit vector. But what it's really asking, they want the bearing in the same form that it was given. That is, how many degrees south of west or north of west or whatever it is, okay, is this airplane going in? Okay, so I need to know what is the angle of that this vector is moving in. Okay? You'll quickly appreciate why we don't use angles. This really is a much better form. It looks kind of nasty right now, but it really is a much better form to work in this rather than having to use angles everywhere. Okay? Vectors are a remarkable mathematical invention. Okay? All right. So let's kind of sketch out what we have here. Both the x and y components of this vector are negative, so I know I'm pointing in this direction somewhere. Okay. The x component is negative 420 minus 25 root 3. The y component is negative 25. And I really want to know this angle here. Okay? If I could find that angle there, I know how many degrees I am south of west. So what do I know here? I know that little trigonometry, tangent of theta, is equal to opposite over adjacent. And now I'm looking for the theta, so let's untangent it. That's arctangent. Arctangent or tangent inverse of negative 25 over negative 420 minus 25 root 3. Okay? That's another calculator problem. Let's plug it into our calculator. I want arctangent of negative 25 over negative 420 minus 25 square root of 3. We are in degrees, so this should give me a degree value. And so our final answer, that angle, is 3.088717. So theta is 3.088717, 318 degrees. I always recommend, by the way, when you're typing these into the app, the homework app, sometimes it says surround, just put the whole thing in, copy and paste the whole thing. Then you don't have to worry about if you rounded enough. Okay? So that's our angle. And so our final answer is the plane is flying 3.0, and I'm going to round to 2 decimals just for our final answer statement, 3.09 degrees south of west. That's where it is actually, that's the direction it's actually flying in terms of the original way the problem described the plane's direction and the wind direction.